Ohayo gozaimasu. Thank you for the invitation to speak. So I'm going to talk about a subject that was active about 20 years ago, about the relation of partition functions of twisted supersymmetric gauge theories to four-manifold invariants, stressing the importance of the U-plane integral. And this is well known to some of you, but it hasn't been very active for 20 years. And so most of this talk is going to be review. There are going to be new results, including results that I arrived at with Yuri Nadayev in a paper last fall, and ongoing work with Jan Manscott. As I said, there's a small community that works on this topic. And so progress is measured on geological timescales. So let's go back to the beginning, to the Cambrian period, when Witten read Donaldson's papers and complex life began. So first of all, what did Donaldson say? So he's talking about invariance of four manifolds, and in this talk, X is going to be a smooth, compact, oriented four-manifold without boundary, and for simplicity, it's going to be simply connected. And so Donaldson studied a gauge theory of a principal SO3 bundle, P over X, and you introduce a metric on X so that you could consider the moduli space of instantons. And then he defines cohomology classes on this moduli space associated to points P and surfaces S in this four-manifold. Now, these cohomology classes only depend on the homology classes of P and S, and they're linear in P and S. And even though the moduli space is non-compact and singular, he makes sense of these integrals. And the main claim to fame of these integrals is that they're metric independent. That means they're smooth invariants of the four-manifold X. And when combined with the beautiful work of Michael Friedman on the topological classification of four-manifolds, that leads to spectacular results on the differential topology of four-manifolds. Now, Witten interpreted Donaldson's construction in a very interesting way, introducing topological field theory on the way. And for a general vector multiplet super Yang-Mills theory with gauge group G, we consider a twisted n equals 2 super Yang-Mills theory. So what the twisting means is we couple to special external gauge fields for certain global symmetries, and they have the result that the fermion fields and the supersymmetry operators are differential forms. And that's important because then the twisted theory makes sense on non-spin manifolds. So a lot of the fun in this theory is, in this subject, is that you want to define it on non-spin manifolds. Among the supersymmetry operators, there's one that squares to 0. It's a scalar. And so we can speak of the Q cohomology of operators, and the correlation functions of these localize to integrals over the moduli spaces of anti-self-dual connections, or generalizations of those moduli spaces, as we'll talk about. Now, Witten's proposal essentially was that for G equals SU2, pure super Yang-Mills, these correlation functions become the Donaldson polynomials. So let me say that a little more precisely. So if Weierstrass P is an invariant polynomial on your Lie algebra, and then you can apply it to the adjoint scalar field in the vector multiplet to get a local operator, which I'll call capital U. And then there's something called the descent formalism that maps from the homology of X, our four-manifold, to the cohomology, the Q cohomology of field space. Under localization, these become cohomology classes on the instanton moduli space, and the composition of these two maps is just Donaldson's mu map. So for example, for SU2, we can take our local operator U of P to be the quadratic Casimir, and the two observable will then be an integral over the surface of trace of phi f. So now we can look at the generating function of the correlation functions of these operators. I'll call that the Donaldson-Witten partition function. And Witten's main statement in his 88 paper was that this is a generating function for the Donaldson polynomials. Here, K is the instanton number, MK is the moduli space of instantons. So that's very nice, but in order to give explicit answers, the strategy here is to evaluate this in the low energy effective theory using the Seiberg-Witten solution. And Witten made a proposal for that answer called in this subject the Witten conjecture. And thereby he introduced the Seiberg-Witten invariance and revolutionized four-manifold theory. So that was a major success in physical mathematics, and we're all very happy about it. Now, it also raises a natural question. Given that success, are there interesting applications of other n equals 2 field theories? After all, the topological twisting only depends on the existence of SU2R symmetry, and so it makes sense for any n equals 2 theory. So we could consider for theory T, as long as we have a local operator, U of P, we could apply the descent formalism to it, and we could consider this generating function of correlators. There might be other interesting correlation functions that are topological. There might be other observables, but at least you have this much. Now, it's possible that this might lead to new four-manifold invariants. It's possible that it will lead not to new four-manifold invariants, but to new relations on old four-manifold invariants. We just don't know. We really don't know at this point. But it's also an interesting exercise in quantum field theory to compute correlation functions of non-trivial theories and non-trivial topologies. So let's look at it. So in this talk, I'm mostly going to be talking about the simplest generalization, SU2 with matter. Matter is defined by a quaternionic representation of the gauge group, and so you can take a number of quark flavors in the fundamental. Each of these has an n equals 2 invariant mass parameter, mf, and in the twisted theory, the scalar fields in that multiplet become sections of S plus tensor E, where E is the rank 2 bundle associated to the principal SO3 bundle P. That sounds pretty funny because SO3 doesn't have a two-dimensional representation. The point is that we're interested in non-spin manifolds. So if we take the 't Hooft flux, W2 of P equals W2 of X, then the product of these two bundles makes sense, even when we don't have a spin manifold. Okay, in the n equals 2 star theory, the quaternionic representation is built from the adjoint. There's one mass parameter, and in this case, you have to use the U1 global symmetry that rotates the quark fields. That corresponds to a line bundle script L there, and if we take C1 of L is W2 of X, then S plus tensor L to the half will make sense. So that also makes sense, and I'll mostly be talking about the case with fundamental flavors in this talk, but at the end of the talk, I hope there's time, I'll say some things about n equals 2 star. So what's the UV interpretation here? So again, we look at this correlation function. It has an expansion in terms of instanton moduli sectors, but now MK is the space of solutions of the generalized monopole equations, where we have some D term, quadratic, and M and M bar. They solve the Dirac equation, and in the U1 case, these are the renowned Seiberg-Witten equations. But in the general case, I don't think there's that much mathematically known about these moduli spaces, and I'm not sure to what extent these integrals have been carefully defined mathematically. Here, E is a kind of obstruction sheaf, so we also have to worry about that. So now I come to the Carboniferous, where the resources that we're going to use with gay abandon and the rest of the talk were created. And in particular, those resources are the Seiberg-Witten derivation of the low-energy effective theory and the U-plane derivation of Witten's conjecture. So let's review that. So first of all, we're trying to evaluate a partition function on a compact manifold, so we need to integrate over vacua. So what is a vacua? The vacua is the Coulomb branch of the theory just on R4. So our adjoint scalar field phi breaks SU2 to U1. We have an order parameter, little u, which is just a complex number. In a general gauge theory, our Coulomb branch would be the complexified Cartan mod the Vol group. Here that's just C. Everywhere on C, the adjoint bundle is broken down to a sum of 3 line bundles. L is the line bundle on which the U1 gauge field is a connection. We have n equals 2 supersymmetry, And so we have holomultiplet. In particular, we have a complex scalar field A on R4. So now all we need to do is compute the couplings, then compute the path integral for that action, and then integrate over the vacuum. So let's do that. So computing the couplings, that's what Seiberg-Witten did, and I think it should be well known to everybody here that the answer can be derived from a holomorphic family of elliptic curves together with a differential. So we'll think of the elliptic curves in Weierstrass form. The differential has the property that if we vary it with respect to u, we get the Néron differential. And the G2 and G3, importantly for this talk, are polynomials in u, in the masses, in the quantum scale, and in the superconformal case, they are also polynomials in modular functions of tau naught. Tau naught is the ultraviolet coupling constant of the UV theory. So, in particular, the discriminant is a polynomial in U, and we can talk about the roots of that polynomial in U. That's the discriminant locus where our elliptic curve degenerates. So let me just jog your memory with, about the examples. And from 1994, this is the first Seiberg-Witten curve. For n equals 2 star, we have this structure here, x minus alpha I. The alpha I is linear in U in the mass squared. The EIs are the Weierstrass function evaluated at the two torsion points. Tau naught, again, is the ultraviolet coupling. The n flavor equals 4 case is rather more complicated. The W's here are the same kinds of factors you see in the n equals 2 star case. But the R2, R4, and R6 are quadratic, quartic, and sextic in the masses. Say more about that in a second. But the point is that the discriminant here is some very complicated sixth-order polynomial in U, and as far as I can tell, there are thousands of terms, and I haven't found anybody who can tell me anything about analytic solutions of the roots. So it'll be important to what I say later that we're not able to write down explicit formulas for the discriminant locus. The masses can be arranged in the carton, an element of the carton of spin 8, and that's very useful because, first of all, those R's are traces in the eight-dimensional representations of powers of M, and importantly, the outer automorphisms of spin 8 is S3, and that's a homomorphic image of SL2Z, so SL2Z acts naturally on the masses. Now, we have a family of elliptic curves, so we have a local system of homology. That's physically the electromagnetic charge lattice, and it has non-trivial monodromy around the discriminant locus. So therefore, you can't have a single low-energy effective theory throughout the U-plane. What you have to do in patches is choose a duality frame, a splitting of the electromagnetic charge lattice, then you have a tau of U, then you can write an action and go and try and compute. So what are the pictures here? So for n flavor equals 0, we have 2 points in the discriminant locus. For n flavor equals 1, 3, or n equals 2 star. For n flavor equals 4, 6. And I wrote little red regions here, not points. And I want you to think of these little red regions as infinitesimal neighborhoods around the points in the discriminant locus. These are the neighborhoods in which the low-energy effective theory breaks down because of strong coupling. Now, we know why it breaks down, pointed out by Seiberg-Witten. It breaks down because new massless states appear associated to BPS states. So the low-energy effective theory in the little red region around some point uj includes charge 1 hypermultiplet, and we, of course, have a vector multiplet, and we introduce it in a duality frame so that the coupling is local. Then we can write an action for the low-energy effective theory in the little red region. So now we're ready to think about evaluating this partition function in the infrared. Here's the ultraviolet version. In the infrared, we're going to have an integral over the vacua on the U-plane, and then there's going to be a delta function contribution from each of the little red regions. Okay, so for example, for n flavor equals 0, there are 2 little red regions. So now we want to make this more explicit as possible. And it turns out that the good thing to do here is to start with the U-plane. So what's the U-plane? So it can be computed explicitly from the low-energy effective theory. Turns out it vanishes for B2 plus bigger than 1. And when B2 plus is equal to 1, it has the following structure. It's an integral over the complex plane of some h, which is holomorphic and metric independent, times psi, which is not holomorphic and metric dependent. The psi is a sum over the line bundles for the U1 photon. The lambda, that's the first Chern class of the line bundle low energy line bundle L. The lambda plus and the lambda minus, those are the self-dual and anti-self-dual projections. That's where the metric dependence comes from. So you should worry about that because topological field theory told you that the answer is supposed to be metric independent. Well, this is just the integrand. So we can still hope that the integral over U will erase the metric dependence. But the integrand is definitely metric dependent. All right, a few comments about Z of U. It's a very subtle integral. It requires careful regularization and definition. It's related to lots of cool things in number theory, which I won't talk about here, but it is also almost a total derivative, and I will come back to that point later on in the talk. But first, let's finish writing down the full answer for the partition function. So what are the contributions from the little red regions? Well, we need to know the low energy effective action in the little red region. And that involves new unknown couplings that you can't look up in Seiberg-Witten's paper. So I'll call those C, P, and E. So E is the coupling to the Euler character, P is the coupling to the signature, and C is a holomorphic coupling to F wedge F. Once you have that, the answer for the path integral of that low energy effective theory is a sum over spin C structures of the Seiberg-Witten invariant for that spin C structure times a certain residue, which has this rather complicated form. For those who are trying to follow the formula, what I'm doing here is AJ is a special coordinate that vanishes at the discriminant point. U, for example, then can be expanded in AJ around that in that little red region. D of lambda is the dimension of Seiberg-Witten moduli space. C squared is 2 chi plus 3 sigma. Okay, now clearly to evaluate this residue, we need to know C, P, and E. So we can't go further until we know that. In principle, C, P, and E could be derived using the methods of the Seiberg-Witten paper, but as far as I know, nobody's ever even attempted to do that. What I did with Witten instead was the following. We observed that if we take the derivative of ZU with respect to metric, as guaranteed by topological field theory, that's the integral of the total derivative. So we can write that as a sum of residues. And we find that ZU is piecewise constant in the space of metrics and discontinuously jumps across real codimension 1 walls in the space of metrics. Now, the jumps at infinity are just those predicted by Donaldson theory, but we argued that the jumps at in the little red regions should cancel the jumps of ZU at the jth point of the discriminant locus should cancel the jump of the contribution of the little red region. We know everything about ZU, so we compute in this way the unknown coupling C, P, and E. Then, for B2 plus bigger than 1, ZU is 0, but now we know C, P, and E, so we can calculate the full partition function. So, you know, we're really interested in the full partition function, but this is why I like the U-plane. It's an incredibly useful technical tool for starting. You start with the U-plane integral, you derive the whole partition function exactly in this way. So I think of this as the Z of U is the tail that wags the dog, and I'm going to call this the tail wagging the dog argument later on. All right, so now we can say what the Witten conjecture is. We've got a formula for all x with B2 plus bigger than 0. For B2 plus bigger than 1, the U-plane integral doesn't contribute, and we get the Witten conjecture, which is an explicit formula for the Donaldson polynomials as a finite sum. The SW of lambda is only non-zero for a finite number of lambda, as a finite sum like this. For those who are following the formulas, chi h is chi plus sigma over 4, c squared is 2 chi plus 3 sigma. So this is very explicit. For example, for K3, it's the simple sign. Now, there's a little cheat here. This is true when x is of what's called Seiberg-Witten simple type. And what Seiberg-Witten simple type means is that the Seiberg-Witten invariant is only non-zero when the moduli space of solutions to the Seiberg-Witten equations is zero-dimensional. Now, all known x, as considered in this talk, all known x with B2 plus bigger than 1 are of Seiberg-Witten simple type, so it's not too strong a restriction. The generalization to the case with flavors is really immediate. So we have a sum over the little red regions, and the contribution of each little red region is a sum of these sum over spin C structures with a residue. And if X is of Seiberg-Witten simple type, then that residue can be computed explicitly as a function of P and S, the masses, the quantum scale, or in the superconformal case, the ultraviolet coupling, from the first order degeneration of the Seiberg-Witten curve. So here's the formula for the partition function. The mu j, to get the mu j, you take the Weierstrass invariant and you evaluate it at the discriminant point. And you divide by this product of differences of the discriminant point. Similarly, the nu j is the Weierstrass invariant at uj to the 1/4 power. This looks rather non-algebraic, and I want to stress that. So first of all, you have to know the zeros of the discriminant, and secondly, there are these fourth powers. So it looks pretty non-algebraic. The f of s is a finite sum of cosines of lambda dot s with that nu j in there. Again, we're using the Seiberg-Witten curve, which is a polynomial in U and Mj. So now we come to the Holocene with the new applications. I think I'm going too fast. I've got 30 minutes. What are the applications? So the first application is just checking S duality of n flavor equals 4. And nobody did that before. We expect it to have modular properties. Here's the formula I just showed you. Mu j and nu j, again, are given by this, and as I was just saying, it's very non-algebraic. You can't solve for the discriminant locus because you've got that sixth-order polynomial with thousands of terms, so what are you going to do? Well, with a little manipulation, you see that as a power series in P and S, the coefficients of any power of P to the L, S to the R, is actually from the sum over the little red regions, a symmetric rational function of the UJs. And then it's easy to show that that means it's nice and modular. And this is the explicit modular transformation law of the n flavor equals 4 theory. So gamma is in SL2Z. It's acting on the ultraviolet parameter. It acts on the masses, as I indicated before. It's like a Jacobi form. It's like a Jacobi form in S and P. S is more like the square of a Jacobi variable. P shifts because of some contact term issues. And there's a non-trivial modular weight. And it's not trivial to get this modular weight. I believe it's 2 chi plus 3 sigma over 2 with 0 multiplier system. So that's the modular transformation law. That's the S duality of n flavor equals 4. Now, as a second application, I want to note that what you can do is you can take these mass parameters. Remember, our Weierstrass invariants are polynomials in the mass parameters. You can take them and you tune them so that points in the discriminant locus collide. And one of the simplest things you can do is make mutually local points collide. So here's a picture for n flavor equals 4. We have 2 strong coupling singularities for large mass, and we're making these 4 mutually local singularities collide. So that means that there's a different low energy effective theory in these 4 little red regions, but they're combining to a single low energy effective theory in some region around this common point. So in formulas, what I'm doing is I'm introducing a mass scale, lambda naught, quantum scale, and it's defined by this equation here. So I'm taking the masses to be large, up to some order 1 corrections, and then the low energy effective theory in that common little red region is just the theory of these light quark hypermultiplets. So the contribution to the partition function should be an SUN flavor equivariant integral over the moduli space, not of Seiberg-Witten equations, but the U1 multi-monopole equation. So this F is a U1 gauge field here, but now we have a sum of monopoles. Each of them solves the Dirac equation. And now it's a straightforward exercise using the formulas I showed you before to pick out the dominant term in this limit, and it looks like this. J is some finite sum of cosines of S, and that nicely agrees with computations of Deduchenko, Kukov, and Putrov of these equivariant integrals on U1 multi-manifold spaces. So it's nice to make a connection with their work in that way. Now, the third application I want to talk about is the AD3 partition function. So let's go to the n flavor equals 1 case. So there's a critical mass so that two singularities collide at a single point in U star, and the Seiberg-Witten curve degenerates to a cusp, y squared equals x cubed. Now, as pointed out in a beautiful paper a long time ago by Argers, Plesser, Seiberg, and Witten, what happens there is two mutually non-local BPS states have vanishing mass. And physically, that means that there's no local Lagrangian for the low energy effective theory, signaling a non-trivial superconformal field theory appearing in the limit as m goes to m star and u goes to u star. So here's the picture. We're tuning m to m star, and then two of our mutually non-local points on the discriminant locus collide. The Seiberg-Witten curve in a scaling region degenerates to this simple form, where lambda squared is m minus m star, and I'll call that the AD3 family of Seiberg-Witten curves. That's very natural from the class S point of view, by the way. So now we can study the AD3 partition function by looking at this particular limit. It's interesting because in this superconformal theory, there's no obvious UV interpretation. So maybe it gives new four-manifold invariance. And in fact, for 20 years, I've been hoping that it would give new four-manifold invariance. So let's see. So for SU2 with one flavor, this U-plane has non-trivial contribution from these little red regions around U plus and U minus, but they're mutually non-local. So that leads to an important subtlety. The limit of the ZU as m goes to m star is not the integral of the limit. And so these don't commute, and we attribute the discrepancy to the contribution of the Argers-Douglas 3 theory. So we know that the limit of the full partition function has to exist because there are no non-compact Higgs branches. The partition function is a sum over all the Q invariant field configurations. The scaling region near U star is governed by the AD3 theory, so therefore that limit of that SU2 n flavor equals 1 partition function must contain the AD3 partition function. It's now a matter of extracting it. So we had an extraction procedure, and what we found to our delight was that that's exactly what you would have gotten by applying the tail wagging the dog argument to the AD3 family of Seiberg-Witten curves and taking the limit as the AD scale goes to 0. So there are two ways to get this answer. They agree, and so the conjecture, the claim, the hope is that this is the AD3 topologically twisted partition function on X for B2 plus bigger than 0. Now, what's the evidence for that? There's not a whole lot of evidence for this conjecture. But one piece of evidence is that just the existence of the limit in the first place is extremely non-trivial and follows from what are called superconformal sum rules. So back in 1998, Marcos Marinho and Grigor Perazza and I pointed out that if the Seiberg-Witten invariance satisfies certain sum rules, then the limit exists. And that's a pretty non-trivial constraint on the Seiberg-Witten invariance. That's an example of new relations on old four-manifold invariance. And it's now a rigorous theorem, thanks to Fian and Lannes, that Seiberg-Witten simple type implies superconformal simple type. So just the existence is non-trivial. That's one piece of evidence. Another one is that we recover the expected U1R selection rule. So the correlation functions from this prescription are only non-zero when the R charges of the point and surface operators, notice they're fractions, we're in the superconformal theory, is equal to a background R charge as computed some years ago by Shapir and Tachikawa. So that's a really good sign that we're on the right track here. So explicitly, we can now be very explicit. Here's the partition function. It's some explicit polynomial in S. Okay, the B here is just some funny combination of Euler character and signature. And a big surprise here is that the point class drops out. Namely, U of P is a null vector. So a priori, this should be a function, this should be a polynomial in P and S, but in fact, the P dependence drops out if X is of Seiberg-Witten type. Seiberg-Witten simple type. So should we be surprised? So Well, maybe not. Already for n flavor equals 0 in Seiberg-Witten simple type, what I showed you before, the Witten conjecture implies that u of p squared minus lambda naught to the fourth is a null vector. But I would take a different philosophical position here. I would say that without a good physics reason for why u of p should be a null vector, I would suspect that it isn't. If there isn't a good physics reason why it's 0, then it ought not to be 0. If it's not 0, that might mean that there's some four-manifold which is not of Seiberg-Witten simple type. That's not math, that's not even physics, that's philosophy. But I'll stick my neck out and predict that there are four-manifolds not of Seiberg-Witten simple type. We don't know it. All right, so I want to come back to this point about the u-plane integral being a total derivative, an integral of a total derivative. So it wants to be a total integral of a total derivative. Here, again, the structure of the u-plane integral is a holomorphic metric-independent function h times psi. I wrote psi approximately before. It's like a Siegel-Narain theta function, but I'm writing it exactly here. And this is something we definitely did not know 20 years ago. So we could put all the metric dependence and non-holomorphic dependence into this total derivative, where e here is an error function. The upper limit is this expression, y is the imaginary part of tau, the metric dependence is in lambda plus and s plus, and what's b? Well, b is anything you like, so long as it's independent of u bar and drops out of the derivative. Now, this is very close to a formula that appeared in a paper of Korpus and Manscott. My student Yuri Nadayev was showing me very similar formulas at the same time. And so this is in our paper. It's slightly different from what's in Korpus and Manscott, but very much in the same spirit. And so that's pretty nice, right? Because now you say, okay, let's just pull the derivative with respect to u bar past the sum over lambda and write the integral as an integral of a total derivative, which would be great because then we can evaluate it explicitly by residues. Because once you reduce it to residues, you can look at the local degeneration of all the various quantities in the theory of the elliptic curve and evaluate things explicitly. But is it true? It's not obviously true because there's no obvious choice for b lambda with both convergence and modular invariance. In our paper, we gave a fallacious argument that in fact it can't be true, but that doesn't mean it is true. Now, what you can say is that the difference for two metrics can be evaluated by residues. That's totally rigorous. So if I take the difference of u-plane integrals for two metrics, characterizing the metric here by the so-called period point, a self-dual two-form, omega and omega naught, then it's the integral of this total derivative, and now this theta function is indefinite theta function, is completely well-defined and suitably modular. Again, this is the upper limit, and it's the modular completion of the indefinite theta functions that have been studied by various analytic number theorists. So this is good because it allows us to talk better than we could 20 years ago about the holomorphic anomaly and the metric dependence. So if we think about theories with a superconformal manifold of couplings, then as u goes to infinity, this theta function here goes to a constant. That constant factors out of the u-plane, but it depends continuously on the metric. So what that means is that the contour integral at infinity means that many topological correlation functions are in fact non-holomorphic in tau naught and depend continuously on the metric, completely violating the predictions of topological field theory. This point was actually made in my paper with Edward Witten, albeit sotto voce. But now I'm saying it loud and clear. So the special case of CP2 has no walls, so we don't see the continuous metric dependence, but what we do see is the holomorphic anomaly. And I want to stress here that we're giving a path integral derivation of the holomorphic anomaly. Because Wafel-Witten partition functions have received a resurgence of interest recently in the mathematics community, there's another topological twist of n equals 4 super Yang-Mills theory, which at least formally computes the Euler character of instanton moduli space. Mathematicians tell me that's not really a topological invariant. The true mathematical meaning of these Wafel-Witten invariants is not completely clear, but there's been a lot of recent work by various mathematicians. trying to clarify that. Now, physics suggests that the partition function in this case is both modular and holomorphic, and to their surprise, when Waffe-Witten used the computations of Klyatko and Yoshioka for CP2, they found that the holomorphic generating function is only Mach modular, not modular. And they noted that a non-holomorphic completion exists, but now there's some tension between the two physics predictions. They can't both be true. So this has never been derived properly from a path integral argument, and the point I want to make is that we just derived a completely analogous result for the n flavor equals 4 theory from a path integral, suggesting that the Waffe-Witten theory will also have continuous metric dependence. And indeed, continuous metric dependence for higher rank Waffe-Witten theories has been predicted in papers of Jan Manscott using other methods. So I think it's an interesting open problem to try and check this using an honest path integral derivation of the Waffe-Witten answers. All right, so let me conclude with some ongoing work. So this is stuff that's going on right now, and everything I'm going to say is going to be much more preliminary. First of all, there's an interesting generalization of all this to invariants of families of four-manifolds. Already in the very early days of Donaldson theory, Donaldson did point out that there are interesting generalizations of his invariants to families of four-manifolds. So, but nobody seems, well, there's some work on it, a little bit of work in the mathematical community and zero work in the physics community. So you can do this physically. So what you want to do is you want to couple to topologically twisted supergravity, and then the result is that the partition function is not going to be polynomials on the homology, but polynomials on the homology valued in cohomology classes of the classifying space of the diffeomorphism group of X, which seems to me interesting because we don't know much about these diffeomorphism groups. So I'm not going to say much more about that, but I want to talk a little bit about the generalization to theories of class S. So many aspects of this are clear, but this is definitely ongoing work. So you can, for class S, you have a U-plane, an analog of the U-plane, so you can ask, what is the U-plane integral? And let me make some comments about it. First of all, it's interesting because the UV interpretation is not clear in general, especially in the kinds of superconformal theories that Davide Gaiato pointed out. These theories might give new four-manifold invariants. Now, that was the motivation for looking at the Argiers-Douglas 3 partition function, and there we wrote it in terms of Seiberg-Witten invariants. We didn't get new four-manifold invariants, but nevertheless, other theories might be more interesting. Now, the U-plane integral is an integral over the base of a Hitchin fibration with a theta function associated to the Hitchin torus. So it's again going to have this general form where H is going to be holomorphic and metric independent, and psi is going to be non-holomorphic and a metric dependent theta function. So what can we say about H and psi? So H is going to have this general form of the coupling to the Euler character has to look like dAdu. The coupling to the signature is delta to the sigma over 8, where delta physical is a holomorphic function on the Hitchin moduli on the Hitchin base, with first order zeros at the loci of the massless BPS states. And the alpha and beta are interesting in principle. In general, they're going to be automorphic forms on the Teichmuller space of the ultraviolet or Gaiato curve C. And I think we don't know anything about those alpha and beta, except in the n flavor equals 4 and n equals 2 star cases. So they are related to correlation functions for fields in a 0 to 2-dimensional quantum field theory that you get by reducing 6-dimensional 0-2 theory on a four-manifold with a Donaldson-Witten twist. That might be a way to get at them, but we don't know anything about those. So what about the theta function? So the theta function is going to have this general form where now the sum over lambda is the sum over torsor for a lattice, which is gamma tensor H2 of X. So gamma is going to be a Lagrangian sublattice of H1 of the Seiberg-Witten curve, and then their characteristics lambda naught and psi, and those are actually important. Psi is especially important, and the reason is that if psi is of the form of something tensor W2 of X, then the wall crossing from the interior of B will be canceled by Seiberg-Witten invariance. That's the tail wagging the dog argument. But what that means is that even in this class S case, we're not going to get new four-manifold invariants. So it's of crucial importance to understand what these characteristics are. So what can we say about these characteristics? Well, the psi really comes from the partition function of a level 1 self-dual 3 form on a 6-manifold of the form of a product of the Seiberg-Witten curve times our 4-manifold X. Now, to quantize the self-dual 3 form, we need to choose a quadratic refinement of the intersection form on the third cohomology. And there are many choices for that quadratic refinement, and they will influence the characteristics. There's a natural choice, which appeared in the papers of Witten on the 5-brane partition function, and were explored more by in a paper I wrote with Dima Bielov. And there, the quadratic refinement is the exponentiated Wu-Chern-Simons action. It's a Chern-Simons action, if you like, of lowest possible level for a 3-form potential. So, so it requires a choice of Wu structure. Now, in this particular case, if we make a weak coupling duality, if we choose a weak coupling duality frame, then a natural choice of spin C structure allows you to evaluate this. It's rather subtle, but I think the answer is indeed that it's proportional to W2 of X. So there are many subtleties here. I might have to retract this, but this is what I think at the moment. Now, I do have a few minutes, so I want to talk about the case of n equals 2 star. So these are the things I can say about the U-plane integral for general class S theories. Even if you've got that all written down, checking that it's single valued is going to be non-trivial. You have to calculate the monodromies of the measure around the discriminant locus. And just to illustrate that point, I want to stress that it's already trivial for n equals 2 star with SU2. So using the tail wagging the dog argument, analogous formulae were worked out for n equals 2 star back in the late 90s, but only in the case when X is spin. As I said, we're really interested in the subject in all 4 manifolds, including non-spin manifolds. Incidentally, Lozano and Labastida did check the S duality for n equals 2 star in the spin case, using a rather different kind of argument from what I gave. For what I gave for n flavor equals 4. The generalization to X which is not spin is non-trivial. If you just copy by hand the expressions from the old papers, you will find that in a non-spin case, the measure is not single valued. Okay? Now, that's not terribly surprising, because I commented before that you had to couple to a U1 baryon number connection. You had to twist the theory by the global symmetry of U1 baryon number rotations. So we've got this external gauge field, a U1 gauge field. Its field strength will be proportional to the first Chern class of the spin C structure you need to choose. And so there should be new interactions after all. Indeed, Shapiro and Tachikawa made this point in their paper. So there should be holomorphic couplings, kappa 1 of U and kappa 2 of U, and so this should fix everything. Well, holomorphy, one-loop singularities, and single valuedness essentially forces this to be the new couplings. And the big surprise here is that it doesn't work. It doesn't work, and the correct version appears to be non-holomorphic. So after a lot of pain and going down wrong roads, Jan and I think we have finally got the measure, and we're currently checking it. So we didn't. Well, actually, we think it's okay now, but that was within the last 24 hours, so it's not ready for this talk. But it's got to be a non-holomorphic coupling, and we're currently checking that the one we have is right. Okay, so it raises the question: does the U-plane integral make sense for any family of Seiberg-Witten curves? This just stresses that it's a really non-trivial question, and I think an interesting one. So I think I'm out of time. So domo arigato.